A never-ending dilemma among software developers and teams using a microservices architecture is whether you should share a database among your microservices or whether you should have isolated databases per microservice. Now, in this video, I'm going to debunk this mysterious question so that once and for all, you know which pattern you should go for depending on your exact use case. So in the first case, where we are sharing a database, we are giving up on isolation. All right, this isolation was the sole purpose of microservices so that different teams with a different deployment cadence don't have any dependency on each other and they can release whenever they want. But now when we have one shared database, we're kind of having a bottleneck here on this API level. I mean, the database is now our API. Now, if this team does a migration, let's say they change the schema, something is going to break for this team, or let's say even if it's the same team, they still have to adjust this microservice as well, because let's say in the worst case, they were actually depending on the same table, right? Maybe it's the same database, but not the same table, then it's not that dramatic, but it is still. But especially if they were relying on the same table, then there's something gonna break for sure for the other microservice. And as you can see, this is not ideal. Now we have one common dependency for these microservices, which is the database. Now, on the other side of the spectrum, we have microservices with their own databases. And this was the original idea of microservices, meaning that this microservice will never access a database that does not belong to itself, meaning this database here. Instead, it's going to use some public API of this other microservice, meaning the API of this service, and then this service is going to either write to this database or retrieve some data for this microservice and so forth. Now, we are giving up a lot in this case, right? This is not a golden standard, because if you do separate your databases per microservice, then if you look at this query and if your application wants to show each customer's last 5 orders with current inventory status, right? It's a common pattern within e-commerce websites, meaning you want to make a distributed transaction like this. So you want to subtract something from the inventory because the purchase has been made, and you also want to charge the customer's card. Then you need to do a lot of work. How can you perform this operation on 2 different microservices? Well, you cannot simply do a join because these are 2 different databases. So what you can do is the following. First of all, you can have one centralized microservice that's going to be kind of an orchestrator, and it's going to do this request, right? And then wait for an answer. After this is done, it can do a request to this service, but this is not going to be ideal. It's going to work for small applications, but if you have a lot of data, if you need to paginate your data on every GET request and so on, this is going to be a nightmare, and I'm assuring you it's going to be a nightmare. So no one is really using this. There's another thing called 2-phase commit, where one service, let's say the same orchestrator service, is going to make a transaction, which is going to start here. So we're going to begin here, we're going to do the debit, and then we're going to charge this service, and then finally we're going to commit. But you know what? Everyone hates this 2-phase commit thingy because it's very unreliable. So as soon as there's an outage or something went wrong in the second service, you're going to have a really hard time reverting all of these changes. So instead, people are defaulting to a pattern called Saga pattern. And I have a video on this if you want to go check it out. Saga pattern basically tells us that we have a message bus, right? Can be RabbitMQ, for example. And what we're going to do is we're going to publish a message to this message bus from the first microservice, let's say the inventory microservice. And then we're going to make a change in our own database. And then this, for example, payment service is going to listen to this specific message, and the message will be subtract amount. And this message is coming exactly from this service. Then it's going to do its own thing. Now, there are 2 patterns within the Saga pattern, which is the orchestrator, meaning we need another service which orchestrates all of that workflow. And there's also choreography, where there is no orchestrator, and all of this communication is done from service to service like I just described. Sagas by themselves are very difficult to begin with, but there's one tricky thing, which is what happens exactly when there's a failure in one of the services. Like the two-phase commit, as we said, is a nightmare. So in Sagas, you have compensating transactions. So let's say this message was picked up by this service, but when we were trying to save this data into the database, some error occurred. Now, we still have the inventory that was changed already. Now, what we need to do is send another compensating message into the queue saying that, hey, by the way, in inventory service, please revert whatever you've done before. And then this inventory service has to adjust its database to the original state again. Now, I'm going to give you a definitive answer on how exactly to overcome these issues, because so far it seems quite complex. But before, let me ask you something. Let's say we have this interesting problem where we have a team of developers, or let's say we're developing a product, and we have 3 different data sources that we need to get our analytics from, or our product data from. We have our own database, a MySQL database. We have our payment data stored in Stripe, and we have our customer data in HubSpot. Fetching all of these 3 different data sources is a nightmare for us. Instead, we can use PostHook, which happens to be the sponsor of our video, and it's going to facilitate all of that for you. PostHook is a developer platform for everyone who wants to build successful products. It basically gives you a ton of useful dev tools that you can incorporate into your flow. So if you want to have this centralized place where all of your data from 50 plus sources is fetched, transformed, and so on, the PostHook customer data platform is ideal for this. And then you can simply use SQL to query all of that data if you want. And if you're developing AI agents or LLMs within your company, and if you want to have this very transparent overview of everything that's happening within your AI agent, be it traces, costs, usages, prompts, and everything, PostHook is also usable there. Just use their SDK in Python, Go, or Node.js, and you're good to go. Not only that, you can also use PostHook for your web analytics and any type of product analytics that you can basically think of. If you're a product owner or project manager, I think you will be really fascinated by the choice that you have. Okay, not only that, but you can also use session replace. You can do experiments. You have a way to toggle on feature flags. You can see logs, error tracing, and of course you can do no-code A/B testing. And last but not least, you can simply install an MCP server on your IDE locally to have access to all of that data from your local AI agent. Fun fact, 90% of people using PostHook are actually using it totally for free, and you can be one of them. So go check out the link in the description, and I'm telling you, you're gonna improve your product with all of this visibility into analytics, error tracking, debugging, AI observability, and so on, and let me know how you like it. And now let's continue. So I'm gonna tell you something very interesting. Everything that we just talked about was not about databases. The database was not the bottleneck all the way. I know this is mind-blowing, but believe me, if we do the domain-driven design, meaning if we split our microservices correctly, then we're almost never gonna run into this issue where we question ourselves whether we should share a database or whether we should not. Now, doesn't mean you have to do domain-driven design and bounded context very thoroughly, but at least if you have this dilemma of sharing or not sharing, then it already smells like you've split your application somehow wrongly. Now, let's look at the way the domain-driven design would split our application. In any DDD, you have something called bounded context, right? And let's say we have 2 bounded contexts, one of them called sales and another one for support. And believe me or not, in 2 different bounded contexts, you can have services with the exact same name. So in sales, you can have a customer service, and in support, you can also have customer service, because customer service means 2 completely different things in 2 different contexts. In sales, it means one thing, and in support, it means a different thing. Now, usually within a bounded context, you would have more chattiness between microservices than not. For example, these 2 microservices would usually communicate with each other much more than communicating with this microservice, which lives in different bounded contexts. Also, bounded contexts are usually split in a way the application is going to access all of this data from the UI, from the client. So at the end, the question we should ask ourselves is, are these services in a bounded context owned by the same team? Then sharing is totally fine, right? Go for it. Are these different contexts, different teams, and they have different deployment cadence, meaning one of the services is deployed every day and another one once a month? Then the database is the coupling that you must break, okay? Don't couple the databases. Now, if you still have doubts and you're not sure which way to go, I'm gonna give you 4 patterns, and I'm gonna assure you that one of them is definitely gonna fit your use case. And this is the one that you most likely gonna choose. So the first one is sharing a database table. Now, keep in mind, this is literally sharing a table, not only the database. And this is probably the worst coupling, right? Don't do that unless you don't want to break your application sometime in the future. Second pattern, and this is probably the best balance out of all. And most of the teams, most of the developers are going to choose this one. And most likely you're also going to fall into this category. We have 2 different microservices, but they're sharing the same database, although they are not sharing the tables or schemas. So this microservice is only going to access this table within the same database, and this one, only this one. Of course, you can also put some constraints so that this microservice literally cannot access the different database, a different table, but in this case, we still haven't done this. And long story short, this is the best scenario for you, most likely. So if you're doubting whether you should share or not share, go for this one. Share a database, but don't share the table. Now, the third one is full isolation with its own drawbacks, as we saw. And finally, we have something called polyglot persistence. And this is a very good use case for not sharing a database. In case if you have different requirements for your microservices, let's say one microservice literally needs a relational database because the data is very structured, and the other database is relying on a graph database like Neo4j, then obviously it makes sense to not share these databases. I hope you guys learned something. If you did, smash like, subscribe for more interesting videos like this one, and I'm gonna see you in the next one. Goodbye.